These are the 4 elements that are required for life as we know it. It's these 4 elements in the exact right amounts that make this planet habitable for us. We have oxygen, carbon, hydrogen, and nitrogen. And we talked a little bit about what each of these does. Oxygen is necessary for all of your cells to live. Carbon, we are carbon water-based beings, and so we are organic, and we have a carbon backbone chain to a lot of our structures. Hydrogen and oxygen together make water. We are also water-based beings. About 70% of what makes us up is water. And then, of course, nitrogen. And we talked yesterday about how a lot of our muscle, our proteins, have a high concentration of nitrogen. In fact, when you eat meat, when you eat skeletal meat, about 16% of that is nitrogen. And nitrogen is very important for protein formation, DNA formation, RNA formation, kidney function. So it's just overall super important. I guess I can make this into an actual PowerPoint. There we go. Our minor elements, calcium, phosphorus, potassium, sulfur, sodium, chloride, magnesium. We're actually going to talk a lot about these in nutrition class. These are inorganic molecules. A lot of them are nutrients that we do need in our diets. For example, like calcium and phosphorus build our bones. Calcium is a neurotransmitter, helps us to clot our blood. Potassium helps regulate muscle contraction. Sodium and chloride. This is going to be table salt, but it also helps us retain water, which is the thing that our bodies do want to do. Also helps us transmit nerve impulses. Then we also have magnesium, which is another component of our bones and also helps us transfer energy. And then our trace elements, I'm not going to go through these. Some of the ones that we'll talk about in nutrition, specifically iron, right, which bonds, makes hemoglobin, bonds with oxygen and carbon dioxide. Let's see here. Zinc is great for skin and wound healing. I think we talked a little yesterday about anti-monkey butt cream, the diaper rash cream, which is fabulous. Slather yourself with it. Put it on the puffies under your eyes. Put it on a burn. Put it on a wound. Put it on sunburn. It's fabulous for everything. Selenium interacts with vitamin E and helps with immunity health. Iodine helps with your thyroid, which regulates your metabolism. So a lot of these nutritionally, they are called trace elements because we don't have to take them in large quantities, but our bodies still need to use them. So then we started talking about atoms, and atoms have 3 components. That's what makes them an atom. If they are missing any of these components, they are not an atom. So we have protons and neutrons. Protons have the positive charge. Neutrons have a neutral charge, and they both live in the nucleus. And then we have our electrons, which have a negative charge, and they live in this cloud around the nucleus. I think we compared them yesterday to a cloud of no-see-ums. I think you call them gnats, where you walk into the little cloud of insects. And so this cloud of electrons is what gives it a more positive or a more negative charge. Together, the protons and the neutrons determine the atomic weight, and that's a really great test question. That would be a great test question. Which of the following components of an atom makes up the atomic weight? So there we go. We just wrote our very first test question. Protons, we just said, have a positive charge. Neutrons are neutral. Electrons are negative, and they have are around in a cloud. And in fact, we have a cloud of electrons around us right now. We are like little atoms. You have these free electrons that are just just floating around the space, and then we can gather them up, and that is what might change our charge. We'll talk about that later when we get into bonding. So these electrons do orbit, but not in a planetary way. They're in a cloud. Here's my interpretive movement for cloud. It's a cloud way. And they can migrate to one side or the other. And what that'll do is it'll actually polarize. Polarize means different charges. And so if we have polarized, it means we have more electrons on one side than the other, which means that one side is going to be a little bit more negative than the other. This is going to be an important thing to think about when we get into things like bonding. So there we got our picture from Big Bang Theory. So it is the number of protons that give it the atomic number. Again, great test question. Which of the following atom components make up the atomic number? And that would be the protons. All right, so now we had a bit of terminology, and that's really just as deep as we're going to go, is just terminology. So if an atom loses an electron or gains an electron, we now refer to it as an ion. Whenever we use the term ion, all we are referring to is it's an atom that has gained or lost an electron. That's it. That's the whole meaning of ion. Ion means I have a different number of electrons than protons. I've either gained one or lost one, depending on what that outer shell's needs were. Now, if in the nucleus I have a different number of protons than neutrons, the term for that is an isotope. So when I use the term isotope, all I'm referring to is an atom that has a different number of protons than neutrons. So that's just the terminology. We're just looking at definitions. Here we had some pictures. Oops. Where is my pen? Trying to find my pen. Where did it go? Hang on. Let me try something here. I don't know why it's not letting me do a pen. Oh well. I guess it doesn't matter. Oh. Stop. Sorry, my everything is freaking out right now. Chat. Oh no, my chat's not working. Yeah, go ahead, Sharon. Try this one more time. Oh, I'm see. Oh gosh, now I've just closed everything. All right, give me just a Zoom recording. All right, so here we have our, wow, Doug fell hard off the wheel on that one. We have some examples. These are our major elements. And you can see here's the shell, and here hydrogen has one little electron. Now, there's not an option to just get rid of that one because then I'm not an atom anymore. So hydrogen's only option is to go find one. And he can either grab one from someone else that's donated it, or more commonly, he's going to go and share one with somebody. We'll talk about that here in just a second. So here we have our carbon, nitrogen, and oxygen. These guys all have a second shell. So we know that it is fulfilled when this first shell has 2, and it is fulfilled when the shells after it have 8. So that's kind of what our goal is. Our ultimate goal is to have 2 on the inner shell and 8 on the outer shell if we have an outer shell. Now, here are some examples of some isotopes. And remember, by definition, an isotope is just an atom that has a different number of neutrons than protons. And here we have some different variations of carbon. And carbon, we're carbon-based beings. Everything on the planet that ever has been or ever will be is a carbon-based being. And it is these different variations of carbon that decay at different times. And so that's when I can dig up the fossil and I can look at the carbon and I know how long it takes that carbon to decay. And that's what tells me how old the fossil is. It's called carbon dating. We're just using isotopes for that.
If it's the protons and neutrons that make up an element, how does it stay that same element if the neutrons are
So it's the protons and neutrons make up the weight of the element. So you can have a different number of protons and neutrons and still have it be the same element, but have its weight be altered.
Gotcha.
So where it is found on the periodic table is where it is stable, where it has the same number of protons, neutrons, and electrons, and has a neutral charge. That's what gives it its place, its atomic weight on the periodic table.
Yeah.
But just because I change, like I get rid of an electron, or I have a different number of protons and neutrons, the element doesn't change. Think of me, I am the element, the major element of Ms. Huff. And if I change my hair to brilliant fuchsia, or I have a facelift, or I change myself in some way, I'm still Ms. Huff. The element ultimately has not changed.
Okay.
Does that make sense?
Yes.
And then the carbon, like 11, carbon 12, carbon 13, those are all just different variations of Miss Huff that has done something to herself to alter herself, but ultimately still carbon. And so depending on how the carbon has been altered, like if we have carbon 11, carbon 12, carbon 13, these all decay at a different rate. And so I can take that carbon, and it is specific to carbon. That's why it's called carbon dating. I look at the carbon and I see how decayed it is, and that can help me determine how old is this thing. So just because we have a different number of components does not change it from being that element. Does that make sense?
Yes.
Good.
Thank you.
So here we have an example of an ion. So here we have sodium, which is Na. Here we have the innermost shell has 2. Our second shell is full with 8. And then sodium has this third shell. And you can see here, there's only one little electron in that shell. So what do you think is easier, me getting rid of that one, or me going around and picking up 7 more? Obviously getting rid of the 1. So that's exactly what I do. I release that 1 electron. So now my outermost shell is this one. I'm trying to do this with my mouse. And it's now complete. I am fulfilled. But just like we just talked about, just because I got rid of that 1 electron does not mean that this is not sodium anymore. It's still sodium, but now it is sodium with a slightly positive charge. If electrons are negative and I get rid of some of that negative, I become more positive. And so now this sodium has a slightly positive charge. Does that make sense to everybody?
So what does that positive charge do?
Nina, I am so happy you asked that. Unicorn high five. Put a pin in that for like 2 seconds, because I'm about to explain exactly why is it important that we know positive charge or negative charge. So a fabulous question. So here's that rate of decay. We're looking at the carbon. How is it decayed? We know exactly how long it takes to decay. And that's how we measure the fossils. When they say carbon dating, that's exactly what they're doing. So the electrons that are in this cloud around the nucleus, that is really what drives the atom. They want those shells to be complete. So the more electrons I need to either trade or share, the more active that atom's going to be. The more active electrons are found on the outer reaches, the less active electrons are found closer to the nucleus. Not all electrons have the same activity level. Some electrons, I anthropomorphize everything. I give human characteristics to literally everything. We got some electrons that are homebodies. They just want to stay on the couch and eat peanut M&Ms and, puffy Cheetos. That's all they want to do. But then we have other electrons that are adventurers, and they want to go on a hike, and they want to go adventure out. This is exactly the same thing as us. Our less active homebody electrons are going to stay close to home, which I consider to be the nucleus. And then our more active electrons are going to venture out and be more active and further away from the nucleus. Now we have two elements who are already fulfilled. Their shells are already full, and they have nothing to seek out. Helium and neon. And because their shells are already full, they don't have anything to prove, they don't have anything to find, we call them inert. And in fact, inert means without activity. So like when you're just sitting on the couch vegetating, watching The Office, like I did last night after I finished all of my own homework, you are inert. So there's your fun new word for today. Oh, I'm just going to sit and be inert. So here we have another example. So you can see here neon, one of our inerts. Here's our innermost shell. We have 1, 2 fulfilled, and then we have 2, 4, 6, 8 satisfied. Everything is great. We have nothing we need to grab. We got nothing we need to share. We can just simply be. All right. When we start mixing stuff together, this is when it gets interesting. And Nina, I am going to answer your question, I promise. It's coming up. When we start talking here in just a second about bonding, how do things bond? That's when our positive and negative charges are going to be super duper important. But first, we're just going to mix some crap together. Let's just see what happens. So when I have a molecule, what a molecule is I've taken elements and I've joined them together. If I have the same elements, I like that sound, joined together, we call that a molecule of that element. So a molecule of the element is multiple elements, but the same element, so multiple numbers of that same element joined together. The bond, that's just the term for how did they get joined together. Are they holding hands? Are they sharing stuff? Are they donating stuff? And then finally, we have compounds. And what a compound is, is two or more elements joined together. But these are different elements. So this is just terminology. That's all I'm looking for. Just terminology. A molecule is when we have atoms bonding together. If they are the same atom elements, they are the molecule of the element. If it is a compound, they are elements that are different. And the bonds is how we join them together.
I love your sound effects.
I know, right?
I mean, they're awesome. And like yesterday, I'm like, burr, 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 burr. I'm like,
Ah, Gina, I'm living rent free right there. After only 2 weeks.
Well, so my daughter's 14. And so I was like, told her, I was like, burp, 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 burp. And she's like, Mom, what are you talking about? I was like, just never mind. Mom. So anyway, love the sound effects.
I need to go get some burpers. That's what I'm going to be doing later. Burp. Although honestly, at this point, you have no idea what's in this can. Oh, I just forgot I'm recording this. It's only Diet Coke. I promise it's only Diet Coke. It's a little early.
Diet Coke is my crap.
Yeah, me too. It's a little early in the day for a burp.
Yeah.
Katie, don't you give me that face. Katie's like, it's 5 o'clock anywhere, somewhere. Man. I love this because you guys forget that I can see you. I love that so much. And I can identify who you are because I'm not looking at you like this.
So just a little note. I have Nayeli and Dylan in my dining room. So I hear what they're saying. And that's why I was laughing.
Well, all right. Well, I can only see like 3, 6, 9, 12. I can only see like 16 of you at a time. Because that's as far as I can expand. Oh, look at that. I can't expand it bigger. Holy smokes. Oh my goodness. I love this so much. Because I have the dual monitors. So I have my PowerPoint and I have you guys on my lower monitor. So when you guys see me doing this, I'm not having a stroke. It's okay.
Dual monitors totally rock. I used to work.
Love it. I love having dual monitors. It is it has changed my life. Changed my life. But
so no wonder you struggle with that little one.
I'm struggling. So that you guys are on my little one on the laptop and my PowerPoint is on the big one. So when you guys see me doing this, I'm not having a stroke. I'm looking at my other PowerPoint. But now I can see you guys.
Earlier. I saw you do it earlier and I was like, I know exactly what she's doing.
I've got like a 32-inch monitor.
Love it.
And it's fabulous. So if you've never done dual monitors, I highly recommend it. It will change your life. So who am I seeing now? Oh, you know what I'm doing? What did I do here?
So you have like 2 computers set up?
All right, so that was a fabulous little brain break. All right, so let's talk about some definitions. Mixture. Guys, this one's not brain surgery. A mixture is when I'm mixing crap together. It's called a mixture. So we have 3 different types of mixtures. And these 3 different types of mixtures are based on a couple of variables. So let me take an example. I have here a glass of water, and I have here a tablespoon of salt. I'm going to mix these 2 things together, creating a what? A mixture. This found in the higher amount is my solvent. So solvent is the word for which one of these 2 things do I have more of. The solute is what I mix into it. Now I'm going to stir this salt into this water and it disappears like magic. But then I set the water down on the table, and what's going to happen after a little while?
It's going to separate?
It's going to settle to the bottom. Absolutely. This water is going to settle, or this salt is going to settle to the bottom. That's kind of the whole point behind these 3 different types of mixtures. All 3 of these, a solution, a colloid, and a suspension, they're all mixtures. But do they separate out or not? That's what gives them these different designations. If it settles out, it's one type of mixture. If it does not settle out, it is a different type of mixture. So the first type of mixture is called a solution. And the solution is a mixture that does not settle out. I have here an example of mineral water. So mineral water is obviously water is the solvent. Minerals are the solute, and they're mixed. They don't reflect light, which is why mineral water is still clear, and they don't settle out. It does not matter how long you leave this mineral water sitting there. It's not like at the end of the day, you're going to have this sandy settlement at the bottom of your bottle. Mineral water is a solution. It does not settle, and the particles are so small they don't reflect light, which means that the mixture itself is clear. So it's literally just a definition. They don't settle out, and the mixture is clear. That equals a solution. A colloid has much larger particles. Now, these particles also do not settle, but they do reflect light, which means that when I have created the mixture, I can't see through it. It's not clear. And the other thing about our colloids is that they can go from liquid to solid and then back from solid to liquid. So this Jell-O is a absolutely perfect analogy for a colloid. You take the water, your solvent, you take the Jell-O packet, your solute, you mix it up, mix, mix. You cannot see through it, right? It is not clear because the particles are much larger and they reflect the light, but they're not going to settle out. And then when I apply a temperature change to it, it changes into a kind of a solid state. And then when I take it to the picnic and leave it in the sun for a while, it goes back to a liquid state. So we've still mixed stuff together, right? We have our solvent and our solute. The definition of a colloid, it still does not settle out, but I cannot see through it. It is reflecting light, and it can transform from a liquid to a solid.
So it's like one substance, basically.
Well, it's two substances that I've mixed together.
So Jell-O would be water in the pouch.
Water and the pouch.
So when it melts, it doesn't separate.
So when it melts, it's not like the salt water. So if I put Jell-O, okay, I have the water, I have the sugar, the Jell-O packet, and I mix it, and I pour that into a cup. And I put the cup in the fridge. And then I have a glass of water and I mix salt, mix. And I put that in the fridge. Even if I pull the Jell-O out and let it melt, let it revert back to a liquid, it's not going to have that Jell-O powder settle out like the salt did. That's what we're looking at for the definitions. Did the solute, or the thing that I mixed into it, did that settle out? That's all we're looking at. Does that make sense? Kinda, sorta. My big recommendation would be this weekend, make each of these. Make like do an experiment. So on your for your solution, you can do salt water, and then you can make some Jell-O for your colloid. And then finally, we have our suspension. And a suspension is a mixture, but the particles are super, super humongous. Great example of our suspension is blood. Your blood is made up, if you want to just do the most basic definition of blood, your blood is made up of fluid and cells. And when you take out your blood and you look at it, you cannot see through it. And if you leave it, the cells are going to settle out. So if we have something that you cannot see through, and you are going to have it settle out, that's going to be a suspension. So let me go in here real quick and do some definitions here. Oops, that did not work the way I wanted it to. All right. Let me, oh, that's getting very warm. Where did it go? I'm trying to do share white screen. Here's my cough syrup. And these are the ones you have to shake well. It says shake well before giving. And that's because it is a mixture that might settle out. And then a compound is just simply different components, different things that are bonded together. So I have this picture here because there are such things as like compounding pharmacies. And so what that is, so let me give you an example. Cats are super hard to give medications to. So if I have a cat that has 2 or 3 different kinds of medication I need to give to it, what I can do is I can go to a pharmacy, a compounding pharmacy, and they can take these 2 or 3 different medications and bond them together into one substance. So now I'm giving multiple medications, but only giving 1 dose. And so compounding pharmacies are fabulous. They help keep you from getting, you know, scratched in the face.
Thank you, Corey.
But
I have a question.
yes, I'm sorry I didn't see you, Katie.
No, you're good. I was trying to let you finish. So what would orange juice be considered, since you have to shake it up, since the pulp sets down at the bottom? Would that be kind of like the salt?
So orange juice, again, not a mixture, but if you had to put a definition on it, it would be similar to a suspension where you shake it up. So especially with my blood, I shake it up. The pulp is then evenly distributed, but I cannot see through it. And then if I leave it, it settles out. That would be a suspension. Although technically, if you want to get super technical, orange juice is not a mixture. Orange juice is a juice. But the pulp does act similar to what we would see in something that was a suspension.
I was just trying to dumb it down for me.
Absolutely, absolutely. So yes, orange juice acts and looks exactly like something that would be classified as a suspension. That's a great analogy. All right, so we've been doing this sound effect that I am now addicted to. It almost sounds like, for any of you that watch The Office, I don't even know if anybody in here watches The Office. I've been an Office addict since it came out on TV. Nina, we are now soulmates, best friends. Because I make Office references constantly, and it's nice to know that at least one person is getting them. So David Wallace.
I watched every episode.
Okay, you suck it. Remember how he was trying to explain it to Michael, and he's like, that's kind of like the noise I'm making right now. So every time I go, it's reminding me of David Wallace and Suck It. Sometimes it's just for me, and that's okay.
Every time you kept saying salt water, I was thinking of sugar water on Men in Black.
Oh my gosh, right?
Yes, because my husband and my brother-in-law will say that randomly to each other just to be weird. So.
Oh gosh. Oh, all right. So we've see, now you're never gonna get that out of your head. We're bonding stuff together now. We're getting complicated. It's getting all sciencey up in here. How do we bond this stuff together? Well, we got a couple of different ways. We've got a couple of different options. We've got covalent bonding and we've got ionic bonding. Now, I know some of you are hearing these words, covalent, ionic, and your instinct is to go curl up in the fetal position and, you know, have a breakdown. It's okay. It's okay. We got this. I got you. I got you. All right, let's talk about covalent bonding first. The way that I remember covalent bonding is just with this little mental, I don't even know where it came from. Sharing is caring, caring is covalent. Every time I think about covalent, I go, sharing is caring, caring is covalent. Because a covalent bond is where we are simply sharing electrons. Nobody has lost one. Nobody has gained one. We are just like, hey, I need one, you need one. Let's share what we have. Okay, and we do. And we can share more than one. We can share 1, 2, or 3, and that would be determining a single covalent, double covalent, triple covalent.
That's H2O, right?
Yes, yes it is. All right, so I want to draw for you now a covalent bond using H2O. So let me see if I can get this. Okay, move you guys. Now I gotta move you guys again somehow. There we go. All right. So let's draw a covalent bond. I have here oxygen. And this oxygen, here's his little nucleus. He's got 2, which satisfies. But then on his outer shell, he's got 1, 2, 3, 4, 5, 6. How many does he want?
8.
He wants 8. And so here I have a hydrogen. And I have 1. How many do I want? 2.
Mhm.
And here I have a hydrogen. And it got 1. And I want 2. So here's what I'm going to do. My 2 little hydrogens come over to oxygen and go, hey, we need 1. And you need, 2. Do you want to just buddy up and just kind of hold hands and share, and we can all benefit from this? And oxygen is like, yes, please. And that's what they do. The hydrogens move closer, and now we just simply share. So now you can see the oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And the hydrogens, 1, 2, 1, 2. Everybody's happy. Everybody is fulfilled. Oh, huzzah. But here's the deal with water. Here's the, let me give you the dealio. See, I'm super street. Dealio. We know that electrons have what charge?
Negative.
They have a negative charge. And you see how we have a crap load of electrons right here? Which means that this area is going to be negative. And do you see how many electrons do we have down here? None. Which means this area is going to be a little bit more positive. We have formed a covalent bond. Sharing is caring, caring is covalent. But what we have also created is something that is polar, meaning that we have 2 areas that have different charges. And this is going to be really important when we start getting this molecule and joining it with other molecules. So, is everybody okay with the covalent bond? And that's water.
You said polar is the 2 areas that are
Yeah.
positive.
So whenever we use the word polar, it means opposite charges. Non-polar means the charges are the same. So polar means I've got one area of one charge, and on the same molecule, an area of a different charge. Polar. Two different charges on the same molecule. Does that make sense to everyone? And that's water. That's water. When we start joining those with other molecules, that's when the magic starts to happen. Oh, it's so fabulous. And time flies when we are having fun. So, wow, that class went by pretty quick. Holy smokes. So we're going to